Hi, and thanks for joining me again today. I'm really glad that you're here. Today's topic is going to be about linear programming. And we've been discussing linear inequalities and systems of linear inequalities. And today is just going to be an extension on that a little bit. So we're going to be graphing more inequalities today. Um, and linear programming is just kind of like I say, an extension of that. It's a tool that we can use to help make decisions. So linear programming is the mathematical process of analyzing a system of inequalities to make the best decisions given the constraints of a situation. And quite often those situations might be manufacturing situations or all sorts of different things. And we will probably want to maximize something based on our materials that we have. So constraints are the restrictions of a situation due to time, money, or materials. We'll take a look at an example here in just a few minutes. But just realize today really is going to be some basic examples. We're going to be working more with story problems in class. And so they're going to be a little more challenging because you're going to have to write the constraints on your own, come up with the objective function on your own, which we'll talk about here in a minute. Um, so it's doing a lot of with story problems. The examples I have today are a little more basic. I just give you the equations and we graph them and solve them from there. Okay. So the feasible region is the common shaded region of the system of inequalities in a linear programming problem. And the objective function is the function to be minimized or maximized using the feasible region. And it's also called the optimization equation. Okay. So hopefully that vocabulary will help you out as we continue here. Okay, so first of all, the vertex principle of linear programming. The vertex principle just is a tool that we can use to help us decide where our system is going to be minimized or maximized. So it tells us if there is a minimum or maximum value of a linear programming objective function, it occurs at one or more of the vertices of the feasible region. So I know we haven't looked at one yet, and we'll look at one here in just a second. But that's where we're looking, is at the vertices. So if you remember when we have graphed systems of linear inequalities before, we graph the lines and we shade a region. And the overlapping region of where we shade is our solution region. Well, now we're going to have probably three or more equations, usually anyway, that we're going to graph. And we're going to look for where those graphs, where the shading overlaps. And then we're going to look at the vertices, or where they cross. And that's really going to be the important point, is where do they cross? So in our first example, from the inequalities graph below, so we have a graph here, find the values that maximize the objective function, and here is the objective function. It is p equals 7x plus 3y. So we're going to find some values of x and y from our graph, and we're going to find which of those values make this the largest, or maximize it. Okay, so if we take a look on our graph, notice the shaded region where they're all overlapping is shaded there. This is the feasible region right here. And so the vertex principle tells us we want to look at where those vertices are. So I have labeled the vertices here for you. We have a vertex at 1, 1.5. We have a vertex at 2.53, and we have a vertex at 4, 0. So what we're going to do is take each of those points and put them into our objective function and see which one is the largest. So if we take, and this kind of demonstrates how I would like to see your answers prepared. So P of 1, 1.5. So if we take 1, 1.5, this point here, we put it in for x and y. So since it's 7x plus 3y, it's 7 times 1 plus 3 times 1.5, which works out to be 7 plus 4.5, which is 11.5. Okay, next one is 2.53. So if we take 2.5 and put it in for x, 3 in for y, we get 17.5 plus 9, which is 26.5. And our 4, 0, we put it in for x and y, so 7 times 4 is 28, plus 3 times 0 is 0, 28 plus 0 is 28. And so now we have to look at, since we're looking at maximizing this, we look at which one of these is the largest. And notice right here, 28 is the biggest value of the three, and so this is the maximum value. So now we just need to write our answer. The 0.40 maximizes the objective function at p equals 28. So notice we say what the point is and what that value, maximum value is for our answer. Okay, so moving on, next example. Graph the system of constraints, name the vertices, and maximize the objective function. So we have a set of constraints here. Notice these two here, x is greater than or equal to 0 and y is greater than or equal to 0. Let's start out with those. So if we look at x is greater than or equal to 0, remember x equals 0 is a vertical line. So if we're looking at greater than or equal to that, it's just going to be over here to the right of the y-axis. And y is greater than or equal to 0, that's going to just put us above the x-axis because y equals 0 is a horizontal line. So it's up here. And so what this does is it tells us that we must be in the first quadrant. And you will see a lot of our linear programming problems have these two constraints. And a lot of these they may not say in the story problem that they're part of your constraints. We just kind of have to know that they are, because let's say it's a problem involving a couple of materials that we're dealing with. And we need to decide how much of each material to use to maximize what we're working with. Well, we're not going to use a negative amount of materials, so each material has to be greater than or equal to 0. And so each axis would represent some material that we have to work with. Okay, so from there, let's take a look here. X plus y is less than or equal to 20. So if we just think it's in standard form, if we graph with intercepts, put in 0 for x, y would be 20. So 0, 20 up here. And if y is 0, x would be 20. So we have 20, 0 over here. And we connect those with a line. And it's less than or equal to, so it is a solid line. And our last one here, y is greater than 3x plus 2. So we have a y-intercept of 2. So I've put a point here at 2. And it has a slope of 3. So if we go up 1, 2, 3, and over 1, 1, 2, 3, and over 1, we can go ahead and draw our line. Okay, now the important thing here is to realize I did not necessarily graph this exactly perfect. So what I've done over on the side here is I've done some side work to help me determine where this vertex is. Where do those lines cross? So if I use equalities for both of these, because we're looking at the lines and we're looking at that point where they cross. So I have the equation x plus y equals 20 and y equals 3x plus 2. And I just got those from this right here. Well, since y is equal to 3x plus 2, I can substitute. So just use substitution. Put it in here for y. So x plus 3x plus 2 equals 20. Combine like terms, 3x plus x is 4x. 20, so 4x plus 2, if we subtract 2 from both sides, we get 4x equals 18. Divide both sides by 4, and we get x is 4.5. So if we put 4.5 back in here, 4.5 plus what is 20? Well, if we take 20 minus 4.5, we get 15.5. So this point here is the point 4, 15.5. Down here we have 0, 2, and we have 0, 0, and over here we have 20, 0. And in here again is our feasible region, but remember we're just looking at the vertices. That's the important places to look. So we have 4 points. We need to take each one of those points and plug them in. Now you can probably tell that these points down here are not going to maximize this. But please go ahead and get into the habit of checking every single point. Even if you kind of know intuitively it's not going to be one that works, go ahead and check it anyway, because sometimes maybe they want the minimum and maximum, or maybe they don't want the maximum, maybe they want the minimum. Um, but just get in the habit of checking all of your vertices. So if we put in 0, 0, 6 times 0 plus 5 times 0 is 0. If we put in 0, 2, 6 times 0 plus 5 times 2 is 0 plus 10, which is 10. If we put in 20, 0, 6 times 20 plus 5 times 0 is 120 plus 0, which is 120. And then the last one, 4.5, 15.5. If we put that in, 6 times 4.5 plus 5 times 15.5. Simplify each of those. 27 plus 77.5 gives us 104.5. So if we look here, the one that maximizes is again this this value right here, 120. So our answer, the points 20, 0, maximizes our objective function at p equals 120. Okay, we'll take a look at one last example here. We have our set of constraints here. So -2 is less than or equal to x is less than or equal to 4. -1 is less than or equal to y, which is less than or equal to 3. And y is greater than or equal to -x plus 2. Okay, so we have our constraints. Let's look at this one first. X is between -2 and 4. So x equals -2 is this vertical line. X equals 4 is this vertical line. So we would shade in between here, but I'm just going to shade the feasible region. I'm not doing all the shading. Here, -1 is less than or equal to y is less than or equal to 3. That just means y is between -1 and 3. So it's this area right in here for each of those horizontal lines. And then y is greater than or equal to -x plus 2. So we have a y-intercept of plus 2, slope of -1. So down 1 over 1, plot a couple more points, and draw our line. And now, since this is greater than or equal to, it's going to be up here. So here is our feasible region. And we have 4 vertices again. We have one here at -1, 3, one at 4, 3, one down here at 4, -1, and one at 3, -1. So I have put all of those in, and over here I have put all of those in. So we have our objective function. If we take each of our points and plug them in, for here we get 2 times -1 plus 7 times 3 plus 4, which gives us 23. Here if we put in 4, 3, we have 2 times 4 plus 7 times 3 plus 4, which is 8 plus 21 plus 4 gives us 33, and so on. So down here, if we put this one in, we end up with 3, and when we put this one in, we end up with 5. So our answer is the maximum value of 33 occurs at 4, 3, and the minimum value of 3 occurs at 3, -1. So there is the answer to that. Again, remember, like I mentioned, we will be doing more complex linear programming problems in class. They will involve some story problems. If you want more examples of those, feel free to look up linear programming on YouTube. There are lots of examples on there. We also have a couple of videos that go along with our textbook. So check out the Prentice Hall website for our textbook. There are 2 examples on there of linear programming as well. And feel free to use your resources if you need more examples. And that's all I have for you today. Thank you once again for joining me, and I'll see you again soon.